today we're going to talk about signal switch architectures, how to choose the right switch and replacing relays and more. My name is Nir Gilger and I'm an application engineer. So the agenda for today, we're going to start with multiplexer basics. Basically, we're going to talk about what is an analog multiplexer, its configuration, and then more. Then we're going to go into multiplexer architectures, the different types of architectures and what are their characteristics. We're going into an overview of each switches and multiplexer features. We go over the features we have in our multiplexers. Then go into our portfolio and our three different sections of our portfolio and what are their characteristics as well. Then we're going to finish up with common use cases, such as the relay replacement, communication protocols, such as I2C, I3C, and full protect application. So let's just start with configuration and operation. As you can see here, there's basically this is a multiplexer. You have a single input, a single output, a 1x1. Also, you have a 2x1. You have two inputs, one output. This is a 2x1 configuration, and you can separate it into channels. So if you have a 2-channel one, you have basically 2 inputs, 2 outputs for 1x1, and 2x1 configuration. You have a 2-channel. You basically have 2 inputs, so basically 4 inputs, 2 outputs. And our multiplexer are also bidirectional, which means it can demux, which also means that an input can also be an output. So you can have an input on A and output on B, and also you can have an output on B and an input on B and output on A. Since our multiplexers are analog multiplexers, they are capable of sending an analog signal as well as a digital signal. So basically here we have an 8x1 switch, an 8x1 multiplexer, 8 inputs, 1 output. Of course, since they're bidirectional, you can also see it as 1 input and 8 outputs. But in this example, we'll use 8 inputs and 1 output. And the way you choose a switch is through these control logic pins. So for example, if I choose pin number 1 or the second pin, A2 and A1 are low, and A0 is high. So number 1 is the one that got picked, the one the switch is closed and passes the signal. Or another quick example, pin number 6, if A2 and A1 are high and A0 are low, 6 is picked, and a signal can go to the switch. So what can a MUX do for you? So MUX can do multiple things. So expand functionality, create new functions, capability, increase access to more peripherals. So as we saw earlier, you can have 8 different inputs into 1 output. So you can have, for example, 8 different sensors going through the switch and switching between them and outputting one of them. Simplify design, eliminate extra components, lessen power, sequence, and complexity. So again, instead of having full components, for example, going for an ADC, you can have them all go to MUX and switch in between them and pick which one goes to the ADC one at a time. Reduce system cost and size. Again, comes with simplified design. If you have less components on your system, your system has a smaller footprint, less devices, the cost is lower. So shrink solution, bigger functionality. And also protection, provide essential system protection, prevent system downtime. So our devices have a lot of protection features that we're going to go into a bit later, but basically they're capable of protecting downstream components in the case of failure or overvoltage or some other cases we'll have a bit later. So the critical parameters for MUX. So this is a little bit of an overview of a basic multiplexer. As you can see, this is 8-to-1, so 8 inputs, 1 output. It has 2 supplies. There's a VDD and a VSS, so this is a dual supply multiplexer, which is capable of positive voltage and negative voltage supply. It has a ground pin, control pins, which control which switches are turned on or off, and the enable pin as well, which basically turns on or off the control pin, the logic pins. So all around, you can see the different parameters we have in our data sheets for each of our multiplexers. So we can start with supply range. This is the supply range of the multiplexer itself. So as you can see, our devices can go up to negative to positive 110 volts. We also have supply current, on resistance, also named R on. This is the internal resistance of the multiplexer. It is basically the resistance between an input pin and an output pin, the path through them, the resistance through that path. There's charge injection, current leakage, control logic, transition time, bandwidth, and the input signal. So how to tell a difference between architectures? So our multiplexers have three different types of architectures in them. Each architecture has its own benefits, pros, and cons. So as you can see on top, this is the NFET architecture. This is basically a single gate. In the middle, you have an NFET architecture with a charge pump. And at the bottom, you see a transmission gate architecture. So you have a PMOS and an NMOS gate. So if we go into the NFET architecture, basically, the way it works, it passes a voltage up to VGS. VGS is the voltage between the gate and the source, and it has to be higher than the VT. So it's higher than VT, the certain voltage, the signal will pass. So a pros for this architecture is the simplest one, since you just have one gate and it has lower capacitance. But the con is it has lower R-on flatness, higher resistance. So as you can see in the graph on the bottom here, as voltage increases, the R-on curve spikes and gets the internal resistance of the device gets much higher as the voltage increases. So features an NFET can do is a down-level translation, which basically could be a logic translator, a logic shifter. A voltage shifter. And going into an NFET plus a charge pump, basically it's capable of rail-to-rail voltages, so it's capable of positive and negative voltage supply, as well as has low resistance and low capacitance and smaller size. So as you can see here at the bottom, the R-on curve is much flatter. So the R-on itself is lower, even though it a little bit increases with voltage increases, but it is much lower. Cons, though, it consumes more power than other architectures due to the charge pump in the architecture. Features beyond the supply switching. This is basically when a device is sending an input higher than it's being supplied. So if the device being supplied with 5 volts and getting an input of 10 volts, it could still work reliably. So this is an example. The TMOS 1511 and 1574. These are devices that have a charge pump architecture in them. And as you can see in the left side, they have low R-on and low C-on. This is due to the architecture, as well as they have some a part-off protection feature that we're going to talk about a little bit later. It can be used for different applications, such as site communication, servers, data center switches, and so forth. And finally, our third architecture is a transmission gate. It also passes rail to rail, so it also can operate in negative and positive voltage. It has a PMOS and an NMOS gate. And as you can see at the bottom of the graph, it also has a flatter R-on curve. So it does have a lower and flat resistance response, but the C-on is higher. The capacitance of the device is higher, and also able to do rail-to-rail switching. So the TMOS 13XX is an example of a device that has that architecture, the transmission gate architecture. And as you can see in the graph right here, the R-on, this is taken from the data sheet of the device. The R-on curve of the device is flat. So going into features of our devices, the first feature we're going to talk about today is 1.8 voltage logic feature. So basically, as you can see here at the top right, you have a microcontroller connected to a switch, one of our devices, a multiplexer, that does not have the 1.8 voltage logic feature. So the MCU, which sends a signal to the logic pins, 1.8 volts logic signal logic to the logic pins, it requires a translator in order to amplify that signal to 2.4 to 3.3 in order to be able to utilize that signal to switch for the switches. But at the bottom, you see a multiplexer that already has that 1.8 voltage feature. So it's embedded inside of it, so there's no need for a translator between the MCU and the multiplexer. So the MCU can just send its 1.8 volt signal to the logic pins of the device, and then the device can pass the voltage signals to its switches and switch accordingly and talk to the downstream components of the system. As you can see, if you don't have a translator on your system, it reduces the footprint on the system and also reduces the cost because you have one less device. Going for our second feature, a phase-safe logic. So this is a protection feature that our devices have. So as you can see, a switch without a fail-safe logic. So the way it works, basically when the device is powered off, the device is turned off, and there's a voltage signal on the logic pin, the select pin. While the device is off, can cause some problems. It can cause either damages to downstream components, as shown here to subsystem B, or it can power up the device, which can cause some unintentional signals on your system. So having a switch with fail-safe logic prevents these issues. So again, when the device is powered off and there's a signal going on the select pin, the 3.3 volt in this example, the device goes into high impedance mode, which basically opens the switch and will not let any signal go through to downstream components and damaging them, and also power back the device and output any unwanted signals. Another protection feature, very similar to the previous one, powered off protection. In this case, also the device is powered off, but this time there is a voltage signal on the input pin or the output of the source pin. In this case, it can also cause some damage either to the device itself, the devices on the downstream devices in your system, or it can backpower the device. And as you can see in the bottom here, in the backpower case, again, you can cause unwanted signal to pass through the switch. But if that switch does have the powered off protection feature, the downstream devices are protected since the device will go into high impedance mode, and it will assure signal isolation when VDD is 0, meaning when the device is off. So since our powered off protection is quite an important and quite big feature we have a slide highlighting kind of the top 5 reasons why you should have a powered off protection. So again, it guarantees when the device is off, it's on high impedance mode, which basically protects the device itself and any other devices on your system from any harmful current caused by power sequencing or hot plug insertion, as well as preventing data acquisition errors by blocking any unwanted signals. And they're very essential in applications such as JTAG. So fall protection, another protection feature. Basically, fall protection is whenever the device is on and there's a signal that is on the source pin or drain pin, on the input pin per se, that is higher or even much higher the VDD or lower the VSS. So for example, VDD is 5, you're getting input of 10 volts, or VSS is negative 5, you're getting input of negative 10. So it can occur for multiple reasons. It can be by an interference, EMC error, or even a lightning strike. So they can be two things. So if the supplies are floating during a fault event without the feature, the switch will get back powered. So you basically have an uncontrolled operation. You have no idea what signal is being output and what's going on. And if the supplies are grounded, the device basically, the switch closes, so it lets the signal through, cause damage to the switch itself and to downstream devices in your system. So when you do have that feature, there are 2 different types. There's the floating type, which basically when you have a high voltage input on your input pin, the device will go into high impedance mode, which means the switch will open and it will not let the voltage signal pass through the downstream components in your system. It won't cause any damage. But this is the floating type, so on the out pin, on the drain pin, it will be floating during that event. The second type, the clamping type, is very similar. Also, you get a voltage signal on your input pin. The device goes to high impedance mode, which blocks that voltage signal to go downstream to damage your components. But this time, your output pin is connected to a pull-up resistor to a set VDD, so it doesn't float. And in the case of the top, as you can see, in the case that you don't have a fault protection in your switch, the high voltage signal will just pass through the switch and cause damage to the switch itself and to downstream components. Go to latch-up immune. So basically, it usually happens in high voltage and high frequency applications. This is TI's new design, created a latch-up immunity feature by using a barrier oxide layer for preventing current flow. So preventing current flow through this gate. So our TMUX, as you can see on the bottom, TMUX 7XSXF and also our ultrasound muxes do have that latch-up immunity feature due to their high frequency and high voltage applications. So another feature, injection current control. So as you can see here in the diagram, S7, the one with the arrow, is the selected pin, meaning we are inputting a wanted signal on pin 7, S7, to go through the drain pin. But we're having an injected current event on the S0 pin. So if you do not have an injection current control feature in your device, and an injecting current event, that current will basically pass through S0, down back to the drain pin, go back to S7, basically causing error in your output signal and distortion and so on. But if you do have injection current control, you have that ESD. So when an injected current event happens, most of that current will flow through that ESD, and only a smaller amount will go through the drain, and you see it on your signal. So a very small error and a small distortion in your output signal. So another example is R-on, so the on resistance of the device and how it affects it, how current injection affects the on resistance of the device and the signal itself. So as you can see here, we have a multiplexer. There are two, it's a 2x1, so you have 2 inputs, 1 output. And S2 is your selected input. So BS2 is the signal you're sending to S2, and you're expecting to see that the same signal will be on D. But you have an injected current event going on S1, and due to that injected current, you're having a delta V error. So instead of seeing that black even graph that you see on S2, you will see the delta V graph, the error, basically with the error. So when you do have the current injection feature in your device, that delta V decreases. So the error decreases. So the voltage signal you see in the drain pin will look very similar to your input voltage you're inputting to the source pin. So we just finished our basically features of our multiplexers, protection features, and now we're going to go into our portfolio. So our portfolio is separated into 3 categories. We have general purpose multiplexers, which are the most cost and size optimized. Some of our key product families, as you can see, is the TMUX 13XX and so on. And in parentheses, it's low voltage and high voltage, LV and HV. And the way we categorize these is LV, low voltage, it's voltage of 5 volts and below, and high voltage is any voltage above 5 volts. So for general purpose muxes, their typical applications could be any protocol communication such as SPI and I2C, as well as MCU sharing and IO extension, and so on. In the middle column, we have our protection muxes portfolio. These are the protection muxes. They have the features we just talked about earlier, all the protection features, such as power off protection, over voltage protection, and so on. And some products to highlight: the TMUX 73XX family, and there's the typical application, again, related to protection, over voltage protection, power off protection, blast protection, and so on. And lastly, our precision muxes. Uh, they are categorized by having very low leakage current and very low R-on, standing for, again, low on resistance. That in order to preserve the signal integrity of the system, you're going to have a more reliable signal with much less distortion in using a precision mux. They also have latch-up immunity for additional protection. Some key products to highlight is the TMUX A1 and A2XX family, and so on. Some typical application, again, precision-related application, precision signal chain, switch and reducer elements, and so on. So when we talked about our portfolio, you can see, for example, now in your, this is, let's say, for example, this is your system. Where can you find these multiplexers in your system? Where can you use them? So for general purpose mux, now we talked about our low cost, can drive protocol signal, communication signals, such as I2C, SPI, and GPIO. You're going to see them around your MCU. They also can be used as logic gates. So they're going to be around this area next to the MCU. Protection muxes, they have all these features we talked about earlier, all these protection features to protect all the downstream components of your system. So they're probably going to be on the edge of the system, on the connectors. And lastly, our precision muxes, they're going to minimize offset and distortion errors. They're probably going to be around the middle area, around the ADC and the gain switch. So that's usually where you find all these three different lines in your system. So now we're going to jump into a little some examples of applications for multiplexers in some different areas. So in the top left, as you can see, you have a multiplexer receiving multiple signals. So you can switch between them, going to an op-amp and the ADC and then to a processor. Next to it, you can have two modems going to a switch, switching between them, going to a single connector. In the top right, a switch is being used as for protection, I/O protection, a series protector on the I/O pins in series. Then the middle left, op-amp gain multiplexing. You can use different resistor values going into the multiplexer for different gain values, depending on your application. In the middle, you have basically you can use it for protocol communication, for SPI, for example. So you have two controllers. You can switch between them to talk to a single peripheral. In the middle right, you have you can use some audio applications. So you have two audio devices as input, outputting to an audio codec. At the bottom left, you have GPIO multiplexing. So you have multiple sensors, multiple temperature sensors going through the multiplexer, and you can switch between them to send to the ADC goes to the processor. Bottom middle, high-speed PHY switch, very similar to the connector interface. You have two PHY signals going in, you switch between them, going to the MAC, and then finally MUX is going to be also using video applications. So if you have like a front camera and a back camera, you would like to switch between them, and you can switch between them and then output the signal to the imaging processor. So this is kind of like more of a general view of applications for multiplexers. Now we're going to go into a little bit more specific and for some photomos. So basically, photomos or a relay is very similar to an analog mux, except it's similar in features, but not similar in architecture. So the way a relay works is you have an LED that emits light when it's being powered, and that light powers smaller photodiodes inside the relay, and that basically powers the gate and sends that voltage signal to the gate. And basically, this slide is kind of a cheat sheet to look into the differences between an analog switch and a photo relay, compare between the two, compare the different terms, what they mean, how they correlate to each other. And an example of our switch, TMUX 8212, compared to a photomos. So as you can see, most switches are smaller than their phonomos counterpart, and they even have better better parameters. So our TMUX 8212 has higher voltage range, smaller RON, and so on. Our devices also can be used for I2C applications. So as you can see, basically there's a bus being split into two. And one big thing in I2C applications, the bus has a limit of 400 picofarads max capacitance. So when you use a multiplexer, you can split that bus into two buses, which means each bus can have its own 400 picofarad bus capacitance, which increases the amount of peripherals you can have on your bus. And you can just switch between them. Also, when you have a lot of SerDes ICs on your I2C bus, they might not have enough unique addresses. So to avoid communication conflict, a MUX can also be used to solve that issue. So as you can see in the bottom left, there are two devices that are suitable for I2C applications. Going into I3C, very similar to I2C, but in I3C, the bus capacitance is, the limit is much lower. It is 50 picofarads compared to 400 in I2C. And as you can see, there's a table at the bottom providing a few of our devices. And the biggest, I guess, parameter to look for is the C-on, the capacitance. Since the limit of the bus is only 50 picofarad, people like a multiplexer also has low capacitance. So for example, the TMUX 136 has a 1.4 picofarad. And TMUX 121 and TMUX 131 have 2 picofarads. So very low on capacitance. So all of these devices are suitable for I3C applications. This is an overvoltage use case, and also in a miswiring event. So a customer basically had a problem with our TMUX 7219. Basically, the problem was that it got back powered. So we replaced it with the TMUX 7412F, which does have the fault protection feature, overvoltage protection. And in that case, it solved their issue and there were no back powering. We do have some application notes in the bottom left that basically explain how overvoltage protection works and how to protect against such events, and some common events that can happen, such as miswiring, such as this one. So lastly, we're going to talk about some fault integration versus discrete. So as we talk about fault protection, so there's one architecture that you can have, that you have your MUX separated from the discrete fault feature, discrete fault protection feature. So you have your MUX by itself to the right, and to the left, you have the discrete fault protection feature. But when the MUX does have a fault protection feature in it, integrated, there's no need for separate discrete fault protection. It's embedded inside the MUX itself. So a MUX without that feature can have outside of it the discrete fault protection architecture, or which a lesser footprint option is a fault protected MUX that has that feature in it and reduces footprint in your system and costs as well. So this is basically the end for today. Conclusion for today's presentation. Sorry. So if you guys have any questions, we'd love to hear them or read them.